If you've managed to assimilate all the information we just covered on the birth and life of stars, then congratulations, you're in a good place with a solid foundation to understand the final stages of stars. So we are now going to embark on learning about degenerate carbon cores, the asymptotic giant branch, planetary nebula, white dwarfs, life as a high mass star, supergiants, advanced nuclear burning, core collapse supernova, neutron stars, and pulsars. Let's begin with a review of low-mass main sequence stars. So we'll come up to speed on that and then carry those through to their final end and then look at high-mass stars and other things as well. We've already covered that the red dwarfs, smaller than 0.4 solar mass, never enter the giant phase. They cycle and burn up all their hydrogen. When it's done, they move down and right to the right on the HR diagram. Their life is over. However, larger mass stars we're talking about, still low mass, but nevertheless larger than red dwarfs, they ascend the giant branch. So after they're done on the main sequence, that's over, then as the helium is contracting, it's heating up, and the star begins to shine by shell hydrogen fusion. So the core shrinks, the outer layers expand, the luminosity increases while the temperature decreases. So it becomes a lot bigger, moves up and to the right on the HR diagram, all the way to the point after reaching about 100 to 1,000 times the original luminosity of the sun. We have the helium flash. Then, that's a significant turning point for the star. It's now settling out and shining by shell hydrogen fusion and core helium fusion at this point, after the helium flash. The core expands, the outer layers shrink down. It expands because the helium is now fusing. The core is no longer inert. Well, the luminosity decreases, the temperature increases, so the star moves to the left and down as it enters into what's called the horizontal branch phase. Eventually all the helium is used up, and when the helium is used up as it's making carbon, then the star starts shining by shell hydrogen fusion and shell helium fusion. And the core is shrinking, the outer layers are expanding again. So this is a new phase in the development of the star that's dominated by its carbon core. And that is what we are now going to investigate further. The helium fusing that is now going on in the core of the star lasts for about 100,000 years, producing carbon and oxygen. It's about 1% of the main sequence lifetime, and it's the triple alpha process, where 3 helium nuclei are coming together to produce carbon. Another fusion of helium will produce oxygen, so less of that, but primarily a carbon core. Now, the carbon is inert. It's not fusing, so it is being crushed by gravity and getting hotter and hotter without an internal pressure from fusion to keep it from being crushed. Getting so hot that it produces a helium burning shell around the core in addition to a hydrogen burning shell, and then fresh hydrogen in the layers above that. So this is a new phase for the star, this double shell burning, and because of that, and the fact that the carbon core is shrinking along with these other shells, the temperature is driven upward, and so the fusion rate is also driven upward. Because the fusion rate is more ferocious, produces more luminosity, expands the outer layers, and for the second and final time, the star ascends up the Hertzsprung-Russell diagram in what is now known as the asymptotic giant branch phase. This is going to be the most luminous the star ever gets in its life. Now the burning question is, can the star fuse the carbon core like it did the helium core that was initiated by the helium flash? Well, keep in mind, the helium ash kicks in terms of fusion at 100 million Kelvin. That was achievable. But 600 million Kelvin is needed to fuse carbon, and before that temperature is reached, degeneracy kicks in, so it keeps it from happening. So no carbon fusion ever happens in the mass range of 0.4 to 8 solar masses. The asymptotic giant branch, or AGB phase, is the most impressive phase of our low-mass star. And here in summary form, we have it rising in luminosity, decreasing in temperature. So this is the direction it's moving on the HR diagram. It's luminous enough to actually be classified as a low-mass red supergiant, even though it's called a giant, usually. The giant branch phase. Well, the star, as I mentioned, is the biggest it's ever going to be, and it blossoms so much during this phase that it literally fills the space in Earth's orbit. It's not fully certain, but it probably will go clear to the edge of Earth's orbit, may or may not engulf the Earth. So the star blows up to a couple of astronomical units, 1 astronomical unit radius. An 8 solar mass star, which is the upper end of the low mass range, will expand all the way to Mars' orbit and literally be 10,000 times the luminosity of the sun. An important part of this phase is what's known as the helium shell flash. So we know we have helium shell fusing, and even though we didn't have a flash of the carbon core, as we just discussed, it turns out that the triple alpha process is very sensitive to temperature. So this helium shell burning is very sensitive to temperature, and the star will go through several phases of that helium shell essentially flashing, the shell itself producing 1,000 times its normal luminosity. Now, that has some significant effects on the star. These flashes essentially cause the star to be a variable at that point. It is increasing and decreasing in luminosity. And so it pushes the outer layers out, and it does this enough to cool the outer layers of the atmosphere until we have electron recombination. We don't have pure ionized gas. And when an electron is recombined into its atom, as you know, that's a decrease in energy of the atom, and it emits a photon. So we have photon emission as a result of that. Well, the photon pressure from the regular shell fusion that's going on, the helium flashes themselves, which is an extra boost of fusion energy and photons, and the recombination. All that pressure is enough to lift the gas from the star. The outer layers are only held loosely anyway, so you have huge, massive stellar winds. And all this instability causes what's called thermal pulsing and dredging in the star. So the carbon that's down in the core is dredged up in part, and literally this huge wind emits carbon smog, and that sounds really bad. It sounds like that's something that we don't want, because you don't want that kind of pollution out in space. But that carbon smog pollution is actually essential for life, because it's what we are made out of. It turns out that through all this process of our low mass star going through all its phases and ultimately having its outer layers puffed off, it can lose 80% of its original mass. And in this last part of the AGB phase, the layers that are puffed off produce what's known as a planetary nebula. And now let's look at the whole picture in one slide, just to kind of give you another shot at understanding the whole process in brief. So here's the evolutionary sequence of a low mass 0.4 to 8 solar mass star. On the main sequence, we'll pick on our sun. It enters the subgiant phase as the core is inert and it produces a hydrogen burning shell, rises up the HR diagram and gains in luminosity. The core is shrinking and getting hotter until it ignites helium fusion in the helium flash, and then stable helium burning occurs until the helium is used up. And we have this hydrogen burning shell. The helium burning core has been shrinking. Once the helium is used up, then it shrinks all the more and enters into the asymptotic giant branch phase, where you have double shell burning and you're producing carbon in the core. And once all the helium essentially is fused into carbon, then the instability takes place with this very bright star, puffs off its outer layers in what's known as a planetary nebula, exposing the core that's within progressively. So you notice that now the star moves way over to the left, very, very hot, but the luminosity is going down because as the layers are puffed off and the very hot core is exposed, the core is really small, so the luminosity is decreasing while the temperature goes up. The dotted line essentially indicates the phase where all that's happening, and then what we have is the white dwarf phase here, and what happens is it's just a core without any fusion and nothing producing energy within it, so it just cools off, moves down to the right on the HR diagram. And that's the life of a low-mass star. Well, if you haven't had enough, a little more detail on that carbon core. After the outer layers are blown away, the exposed core is so hot that it can literally ionize the gas around it that it puffed off, producing a planetary nebula. And here is the spirograph nebula. Look how pretty it is. Some very beautiful nebula are seen with our current very powerful telescopes. And note that planetary nebula has nothing to do with planets, yet if you look at this, you can imagine that older telescopes that weren't taking images this nice might have mistaken these objects for planets. They look like they have some, in some cases at least, roundish features. Looks a little bit like the planet Uranus at times, and you know, they tend to be very far away. So the name stuck, even though, as we've seen, it's all about the evolution of a star, nothing about the planets. Well, it's remnants of stars with masses up to 8 solar masses. And the radii themselves are up to 3 light years, so they expand out quite a bit at about 20 or 30 kilometers per second, the rate at which the gas expands. After about 50,000 years, they've dispersed so much that you basically don't see them. There are tens of thousands of planetary nebulae in the Milky Way galaxy. The fact that they don't last more than about 50,000 years means that there's a lot of them going off on a regular basis. About 5 solar masses per year of gas and dust is recycled into the galaxy. And this actually accounts for 85% of all the matter expelled by the stars, including the supernova. And of course, we know that galaxies are all about recycling gas. So this is material that is then available in the interstellar medium to produce additional high metal population 1 stars, because this isn't just hydrogen and helium that's being puffed off. You have the enriched metal content as well. The exposed core in the center is known as a white dwarf. So here's a really clear image of that object. It's hot and small in radius, obviously because it's that extremely bright stellar core. Supported by degeneracy pressure, stalemate with gravity, it remains in that condition for billions and even trillions of years. We actually haven't seen one that's actually cooled off. The universe isn't old enough to have produced white dwarfs that are old enough to have cooled off sufficiently, because it takes many billions of years for them to cool. It needs a lot of time. So to give you an idea how planetary nebula form, we have a couple stages. In brief, stage 1, you have this thick layer of gas. The red giant is huge, and it still has most of its mass. So initially, to blow off the layers, it encounters more resistance. Therefore, the wind and the gas that's blown off is slower initially. Well, stage 2, after some of the outer layers are blown off and it's not so thick anymore, then the layers underneath can move with greater velocities. They don't encounter as much resistance, so they're more energetic, and they collide with the slower moving layers and produce ionization as a result of that frictional impact, along with the fact that the hot core has got the photonic energy to ionize the gas. So the combination of those two things light up the nebula in layers, producing the beautiful and often very complex series of concentric shells and other geometric shapes lighting up the nebula. Just a few examples of some beautiful planetary nebula. Here's the Helix Nebula. Notice the white dwarf right in the center. The Ring Nebula in Lyrae. Notice the red hydrogen emission and the green oxygen emission. The Eskimo Nebula. Notice the fur ruff. The Dumbbell Nebula. The Fetus Nebula. If you look real closely, you can see a heart beating in here. NGC 2818. Very complex structures here. Speaking of complex, the Cat's Eye Nebula. It's still not understood all the various processes and historical sequences that took place to produce this particular planetary nebula. Here's another image of it with different wavelengths being colored uniquely here. And a whole bunch of additional examples. And this is only a handful of all the many planetary nebula that we can image in our Milky Way galaxy. I'll finish our first part here by just considering the implications for Earth from all these incredible changes that the sun is going to go through. Some massive changes we discussed here. So here is changes in the sun's luminosity over time. So it's a rather complex sequence. And this is the luminosity, a logarithmic graph. So here's now one solar luminosity, 10, 100, 1,000, 10,000. So this rises very rapidly. People like to speculate as to, what's the fate of humans in the future, and that's a very interesting topic to discuss. But just in terms of the raw reality of the evolution of the sun, we can certainly put some limits on what we can expect for our future. The stages are all shown here that we discussed. Now the sun has already brightened by about 30% in the last 5 billion years. So from the beginning to now, 30%. And it doesn't seem like much is happening along here. But this is the main sequence time for the sun. And all the craziness we've been discussing lately is over here with a different time scale that you might notice. It all happens very quickly. So this scale is not uniform. But the current brightening of the sun is actually going to be very significant. It's going to eventually overwhelm Earth's greenhouse gas regulating scheme, where carbon could be removed from the atmosphere and subducted in the Earth and cause the brightening of the sun not to cause the Earth to get too hot. But it's not so much of what's going to happen way in the future here during the death of the star itself. More interesting is what's going to happen along this main sequence. How long can we survive along here? Well, it turns out that in the next billion years, when the sun goes from here to here, it's questionable whether the oceans will survive. They may evaporate. But even if they haven't, by the time we get to here, certainly we won't have any oceans left. The oceans will have boiled away. Any greenhouse gas regulating process that the Earth can handle? Nope. The solar luminosity will completely overwhelm it. So that's a little bit sobering. But just before the helium flash, the sun is going to be over 1,000 times more luminous. The Earth will literally heat up to about 1,000 K. That's not very conducive for life. We won't be here at that point. At the end of the AGB phase, the sun will be thousands of times more luminous, ejecting its layers, producing the planetary nebula. At that stage, if the Earth has not been completely destroyed by the AGB star literally engulfing the Earth, certainly its charred remains will dim in the twilight of the fading white dwarf. And it's justified being a little poetic here because of the gravity of the prognosis for our poor but beautiful planet Earth.